What's going on? It's Justin Dickmeyer from engineerintrainingexam.com, and in this video we will review how to solve simultaneous linear equations using matrices. Say we are given a number of linear equations, each with a set of unknowns such as ax1 plus bx2 plus cx3 plus zxn is equal to y1. We're given another equation, dx1 plus ex2 plus fx3 plus all the way to yxn is equal to y2. And then finally we're given gx1 plus hx2 plus ix3 all the way to xn, and that's equal to y3. So this is our set of linear equations. Now x1, x2, and x3 are our unknown values. A, B, C, all the way to Z are known coefficients in the equations, and y1, y2, and y3 are also known quantities. So if we're given any set of linear equations in this format, we can express it in a compact matrix AX is equal to Y, where A is going to be it's going to be a square matrix with as many columns as there are unknowns and rows as there are equations. X is going to be a single column vector matrix with as many rows as there are equations, and Y is also going to be a single column matrix with as many rows as known Y values. So the process boils down to this. The process of solving simultaneous linear equations using matrices is: number one, express the set of linear equations in the compact matrix form AX is equal to Y. So we need to express set of equations in AX is equal to Y. Our second step is then to pre-multiply both sides by the inverse matrix of A. So pre-multiply both sides by the inverse matrix of A. So that gives us the inverse matrix of A times AX is equal to inverse matrix AY. We're pre-multiplying both sides by the inverse matrix of A. And number three, since we know that this operation right here, the inverse matrix of A times A is equal to the identity matrix I times the matrix X, which is equal to X, because the identity matrix does not change the form of any matrix. We're going to get a new matrix after we carry out this operation. X is equal to the inverse matrix of A times Y. And once we do this operation right here, we will get a single column vector matrix with all of our values in this single column X right here. So as long as the inverse matrix A exists, we can solve for all the unknown X values. If the inverse does not exist, then the set of equations does not have a unique solution. So let's reinforce this concept with an example. Say we are given the set of linear equations X plus 2Y minus Z is equal to 6, 3x plus 5y minus z is equal to 2. And finally, negative 2x minus y minus 2z is equal to 4. So what we want to do here is solve for all the unknowns x, y, and z using our matrix format. So we know that our first step is to we want to express this set of linear equations in the form ax is equal to y. So our first matrix A is going to be a 3 by 3 matrix because there's 3 unknowns, x, y, and z, and 3 equations. So what we do is we just take the coefficients from the first equation and put that as row 1 in our new matrix, and the coefficients from equation 2 will be our unknowns in our second equation. So let's go ahead and just express that here. We got 1, 2, negative 1, 3, 5, negative 1, and negative 2, negative 1, and negative 2. So let's do our x vector, single column vector matrix here. Those are just our unknowns, x, y, and z. And that is going to equal our single column vector matrix here of 6, 2, and 4. And these are just our known y values on the right side. So now we have our linear equations set up in our matrix format that we need. And now our second step is to pre-multiply each side by the inverse matrix of A. So the first thing we need to do is determine whether A has an inverse or not. And we can do that quickly using the method of cofactors. So recall that the determinant, whether this matrix has a determinant or not, is going to tell us whether or not there is an inverse of this matrix. So the determinant of A using the method of cofactors is 1 times negative 10 minus 1 minus 2 times negative 6 minus 2 plus negative 1 times negative 3 minus 10. And calculating all that out, we'll get that the determinant is negative 2, so it does exist, which means that there is an inverse. Now, I've already worked the inverse out here, so I'll show you guys that the inverse of matrix A is 5.5, negative 2.5, negative 1.5, negative 4, 2, 1, negative 3.5, 1.5, and 0.5. So this is our inverse matrix of A. So what we need to do now is take this inverse and pre-multiply both sides of this equation by that inverse matrix, and we will get our values for x. Now let's play that out. So pre-multiplying, let's just skip the step number 3. We know once we pre-multiply that we're going to get a new matrix form in the format of x is equal to the inverse matrix of A times y. So our x value single column vector matrix is x, y, z is equal to our inverse matrix of A, which is 5.5, negative 2.5, negative 1.5, negative 4, 2, 1, negative 3.5, 1.5, and 0.5. And our single column vector matrix are our y values, which is 6, 2, 4. So now we're at the point where we can just solve for our values of x, y, and z using matrix multiplication. So let's go ahead and determine what we're going to get here. We're going to get a single column matrix as our answer. And through matrix multiplication, we go 5.5 times 6 plus negative 2.5 times 2 plus negative 1.5 times 4, and that will give us our first value of 22. And then just carrying out basic matrix multiplication, again we get 22, negative 16, negative 16. So that tells us that for the set of unknown values that we were given at the very beginning, or the set of linear equations, let's go ahead and write those out again. X plus 2y minus z is equal to 6. 3x plus 5y minus z is equal to 2. And negative 2x minus y minus 2z is equal to 4. So given this set of linear equations through a matrix form, we solved for the unknown values x, y, and z. X is equal to 22, y is equal to negative 16, and z is equal to negative 16. So any set of linear equations with unknowns can be solved using matrices just as this. So that's it, guys. I hope that clarifies the process of solving simultaneous linear equations using matrices. You guys hop on over to my website at engineerintrainingexam.com and send me a contact with some feedback. Let me know how I'm doing over here. If you guys have any suggestions or comments, I also welcome those as well. So you guys take care, and we'll be talking soon. All right, bye.